Alright, so let's catch up to where we were before and move on. We're going to start with our vector space V and its dual space V dual, V star. And of course the vector space V will have a basis, and as always there's a four-dimensional vector space. It's a real vector space, and the dual space has its associated dual basis E mu like this, and we know of course that the dual space basis is related to the vector space basis through the relationship that the dual space mappings, well, I'll make that nu, E nu equals delta mu nu. And this vector space, the underlying vector space, we are going to promote, I love using that word, we're going to promote to an inner product space by establishing an inner product that we define this way, E sub mu, E sub nu. And this inner product is a map, well, it's essentially a function that takes two vectors and produces a real number. And once we know it for the basis, we know it for the entire vector space. So in order to define this thing, I have to define the following quantities. I have to define E0 equals something, E1 equals something, E0, whoops, actually that's E0 E1, E0 E2 equals something, E0 E3 equals something. And I have to do this for every possible combination of E mu and E nu. So I got to do this, create the same thing for E1, E2, and E3. And I might just, to exemplify that, I'll do E1 out. E1, 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 E2, and E1, E3. And obviously I need to do the same thing for E2, E0, etc. And then E3, E0, all the way, and then the last one will be E3, E3. And once I choose these numbers, I have defined an inner product space, because now I have a vector space which has its vectors addition and scalar multiplication and all those things. I have an inner product because I've written it all out, and I that definition of an inner product attached to this space gives me a vector, or a inner product space, and that's what V is now. Now the dual space does not have an inner product, because the inner product is a member of the vector space, not of the dual space. So we still can't just crank out and compare dual vectors. However, we're very close to being able to do that, because what we need to notice is that there's also the following tensor product space. We know that this tensor product space exists, and we know that every element of this tensor product space looks like a fully contravariant component times, oops, geez, what am I doing? A fully covariant component times an element of the basis, where now this is a basis of the inner product space of the tensor product space, and this is the component of the tensor product space. And there are 4 times 4, there are 16 of these. Notice that there are 16 of these also. And that's an important point. This is an object that takes a map. This is a map, so I can actually, let me write it as a map. TAB E alpha E beta is a map that goes from V cross V to the real numbers. It goes from the Cartesian product of the vector space to the real numbers. Well, what does this do? This takes two vectors and goes to the real numbers, because I have to put real numbers in all of these slots. So this is actually a map from V cross V to the real numbers. I know because this takes a vector, this takes a vector. Well, that's a mapping to the real numbers, right? This is actually the way I've written it here. This is a specific mapping that takes the specific vector e mu, or the specific pair e mu e nu, right? And this gives you the real number associated with that. That's what this specific map does. I guess to be more correct, I should erase this and just say this inner product, this operation, is a map from V cross V to the real numbers. That's what I really mean. But the point is, I have two ways of mapping things from the Cartesian product of the vector space to the real numbers. One is I have this inner product, which will do it. And two, I have an entire space of an infinite number of maps, any one of which will do the same thing. So the obvious question that comes to mind is, can I find a map here that duplicates this? And the answer is sure. If I happen to choose the map where these components equal these values, I'll have found the same mapping in the dual space that executes what the inner product space does. So let's pick this. Let's pick these numbers here. Let's say I call this number G00, and I call this G01, and I call this G02, and I call this G03. These are numbers that I have to pick to make my inner product work. G10, G11, G12, G13, and I'd call that G20, and I'd call that G30, and I would call that G33. Like that. Well, if I pick the mapping in the dual space that looks like G alpha beta E alpha cross E beta, if I took that mapping and I took this inner product, how do they compare? Well, the inner product, let's take two arbitrary vectors. The first arbitrary vector will be A mu, E mu, B nu, E nu, like that. Well, I know that that's going to be A mu, B mu, E mu, E nu, and that is going to ultimately equal, when I pull out all of the sums, that is going to ultimately equal A mu B nu times G mu nu, because these things here are all replaced by these things here, and I have all these subscripts really ready to sort of execute this, but it's a sum. A1, A00, E00 will equal A00 times E00, which is G00. Let me make that 0 there look a little better. So that's what this inner product will equal, right? But what about if we just use this dual space mapping? Well, if we use this dual space mapping, we get G alpha beta times E alpha E beta. This thing is a map, and it's going to act on A mu, E mu, B nu, E nu. Oops, I've got to get my indices to match, right? I've got to get my, well, no, I don't, actually. I don't need to get my indices to match. So it has to look like that. And then this is going to end up being G alpha beta, because it's linear, so it comes out, and it's E alpha times A mu E mu times E beta B nu E nu. And this here is going to act in a completely linear way. So this will be A mu, and I'll pull out the B from here, B nu G alpha beta E alpha E mu E beta E nu. But this thing is delta alpha mu, and this thing is delta beta nu, so we get A alpha B beta G alpha beta. And this exactly equals this. So by choosing the components of the tensor that lives inside the tensor product space, lives inside our tensor product space, by choosing those components to mimic the inner product, we have now selected one special tensor in the dual space that maps just like the inner product would map. And that is suddenly sort of breaking our symmetry in a sense. It's breaking our promise to consider everything in this space to be equal. Now we found something that we like in particular, but we didn't really find it in here. What we did is we promoted this to an inner product space, and we created an inner product to make that promotion happen. And it turns out that that creation is just mimicked by one particular tensor that lives in the tensor product space. That particular tensor is called the metric tensor. And it is the most important object in elementary special or general relativity. It's called the metric tensor. Now, it could have gone the other way, right? We could have done this the other way. We could have looked in this space and said, you know what? I like this map. This one particular map is the most important map. I'm going to pull that out and call it the most important map and give it some kind of special status. I'm going to use that map to take two vectors from the basic vector space, and I'm going to use that to measure all these vectors. Meaning I'm going to be able to take two vectors, get a real number out, and it's going to follow all the rules that we talked about last time. And so I'm going to start with that. And then I can say, well, you know, that's the same as having an inner product, right? And I could have created this inner product after I'd picked this map. Doesn't really matter. The point is it's completely equivalent, even though I've kind of introduced it this way. So I could call this a metric space. I could call this vector space with a metric. I could say this is an inner product space. But regardless, once I do it, this is automatic. If I pick this, I immediately have this, because all I have to do is just, I know that there is a mapping out there that performs that inner product mapping, and likewise, there's an inner product that mimics this, that mimics a favored metric tensor. Okay, so now we're going to use our first, now that we have this, now that we've created this metric tensor and created this inner product, we're really going to lean now on the metric tensor definition. That's what we're going to talk about mostly. But understand that this metric tensor was this preferred thing that popped out because of the need for an inner product which was attached to V, which would allow us to measure vectors. In fact, that's why it's called a metric, right? The idea of the metric is that it measures something. And you have vectors in the vector space, you need two of them, you want to compare them, you want to measure them. So if we stick two of them in here, we get a real number out, right? If we stick the same vector in here, we should get a real number that represents perhaps the magnitude squared of those vectors. Or if we compare two different vectors in here, we get a real number out that tells us something about the relative nature or the relative way of comparing those two vectors. But it's arbitrary, right? We still are picking it, but we're going to usually use this mapping. But what's very important about this is going back a step where I said before in a previous lecture, despite the fact that all we created was the vector space and now the inner product space, the dual space pops into existence just out of sheer logic alone, right? There's no way, however, to take any vector in the vector space and associate it with a covector. Even these bases sort of look associated, but they're associated through this sort of random rule we made, which you can see how convenient the rule is, right? It allowed us to throw down this delta function down here. So it's not completely random in the sense that it's chosen with totally arbitrary. But if this rule had been different, if I had chosen a basis where this wasn't a delta function, it was something else, I would have just ultimately had to squeeze in something else here instead of the delta functions. using the delta functions gives us this nice mechanic to how all this works, but it's still arbitrary. So if I mean by arbitrary, meaning if I take an arbitrary vector in V, I can't find a immediately correlated vector in the dual space. You know, even if I wrote this, right, and said, oh, I'm going to take all of the components and I'm just going to create the dual vector with the same components, they're not really, that's not really a connection. That's just, of course there's a vector here that has the same components. Oops, of course there's a vector here that has the same components as a vector here. The fact is they're not related in any way. So let's have a look at how that is just suddenly changed. That is all changed. Because in our vector space and in our dual space, we now have a metric tensor. G mu nu, E mu, E nu. There's our metric tensor. I'm going to put a little box around it. Right? So now, look what happens when I choose a vector in our vector space, an arbitrary vector in our vector space. I'm going to take that thing and I'm going to now find a connection, a connected vector here. And that connection is going to be established by the metric, meaning I have this vector, this metric is going to help me pick out a vector in the dual space that's related to this thing. And it's pretty straightforward, actually. I write G mu nu, E mu, E nu. This is a map, and I'm going to act on A alpha, E alpha, E alpha. But I'm going to leave this blank, right? I'm not going to put anything in here, which means I'm taking a map that's looking for two vectors, because this is a map that takes a vector, this is a map that takes a vector, and this whole thing is looking for an ordered pair of vectors. But I'm only going to give it one right now, and I'm going to leave this blank. And it can still feed on the one, it just won't return a real number, right? So what will it return? It will return G mu nu times A alpha, E mu, E alpha, right? That completes the first half of the mapping. But the second half of the mapping is going to be E nu blank. It's a real number. It's a real number, but it's a real number that's waiting for a vector. This will be a real number once it gets a vector. This is a real number. It's the delta function. We know what that's going to be. And of course, these are real numbers. So the next step, I'll just work it out real fast in advance, right? This delta function mu nu converts the alpha to a mu, and you get alpha mu, G mu nu. This is now gone, and you're left with this thing. But this thing is essentially a map. It's a map that's looking for a vector. So, and you'll notice now that, so this is actually just, what is this map? Well, that map is E mu. That's what E mu does. E nu, sorry. That's what E nu does. So this is what's left. And remember, this is a covector here, right? This is a real number. And the number of indices works out because if you look, this is a contraction. This is a contraction. So this thing here has one free index, this nu, which of course is contracted with that. So this thing here and this are an element of the dual space. And what we do is, this is so important, it happens so often, that if you have the metric tensor, if you contract against the metric tensor, we say, oh, let's just redefine this into something a little more convenient. Let's just eliminate the contracted index, and we'll just call this A nu, and then this of course stays E nu, and this is what is left over after you punch in only half of what the metric tensor is looking for. You're left with something that's still sitting around waiting for another vector, which is exactly what this is doing. It is that's the mapping that's waiting for another vector to map, and these are the components of that mapping, and it's all living in the dual space, right? And the reason we give it a subscript is now we're going to say, oh, the metric tensor, this contraction just eliminates that. But what we'll agree on is that if I have a lower index on A, that's going to mean that we've contracted the object with the upper index against the metric tensor. And that is the origin of this notion of lowering indices and the notion of lowering indices with the metric tensor. And you can see why it takes the metric tensor to do it. You have to have this special tensor that we agree on is unique. And once we've done that, now we do have a connection. We do have A mu E nu. And this thing is now called the, well, we call this the contravariant form of A, and this is the covariant form of A, but it only makes sense after you've defined the metric tensor. If you haven't defined the metric tensor, you can't do this. You can't go through this whole exercise to get to here. And what's ironic, of course, is that we're talking about the components. So these are contravariant components, and we've already explained why. It has to do with their transformation properties. And these are covariant components. But make no mistake, this is still a vector that lives in the dual space, so it's actually a covector relative to these things, which are vectors that live in the vector space. But what's so critical is to understand that this only makes sense. This covariant form of a vector, the covariant form and the contravariant form only can exist after we've pulled out this metric tensor map. And the reason this raising and lowering of indices works at all is because of this process. Now, there's absolutely nothing to stop this process from working for higher order tensors, right? If this will lower the index of components of higher order tensors, and I'll quickly demonstrate that next time.